scratch.
Hello again. In our last video, we introduced the concept of set and cardinality. Let's dig a bit more. The membership relations regarding sets are based on the connection between an object and a set. For instance, let P be the set of the planets Mercury, Venus, and Earth. The planet Venus is an element of the set P, so we may write, Venus belongs to the set Mercury, Venus and Earth, or Venus belongs to P. The planet Mars, however, is not an element of the set P, so we write, Mars doesn't belong to the set Mercury, Venus and Earth, or Mars doesn't belong to P. We can read the symbol epsilon in several different ways. Regarding the element Venus and the set P, we can read, Venus belongs to P, Venus is an element of P, or simply, Venus is in P. If we want to talk about the element Mars, we can read, Mars doesn't belong to P, Mars is not an element of P, or simply, Mars is not in P. Mathematics is an exact subject, and one of the main concerns when we are building a theory, is the rigorous descriptions. That's why I'm telling you about the different ways of reading Venus belongs to P, or Mars doesn't belong to P. By the way, we may write like this, and say that P owns Venus, P has the element Venus, or simply, P has Venus, and P doesn't own Mars, P doesn't have the element Mars, or simply, P doesn't have Mars. After we declare some definitions, we may construct some laws, which are consequences of those very definitions. We did that already in the first video, in a casual way. Those laws are actually called theorems. And here is your first formally named theorem. There is no object, let's call it X, that belongs to the empty set. If the previous statement is a theorem, we need to prove it. That's right. There is essentially what a theorem is a law that can be proved by the definitions we previously declared. But how? How do we prove that there's no such object that belongs to the empty set? Take a look at the following. Let's assume there is such an object, let's call it X, that belongs to the empty set. But, if X belongs to the empty set, what can we say about its cardinality? Well, we don't know for sure. But we know that, if X belongs to the empty set, its cardinality is, at least, 1. But, how can that be true? How can the cardinality of the empty set be at least 1, since we learned that its cardinality is equal to 0? Well, it can't. We reached a contradiction by assuming that X belongs to the empty set. And so we proved there's no object X that belongs to the empty set. The QED we wrote at the end of the last sentence, means quod erat demonstrandum. It means, which was to be demonstrated. We should always write QED at the end of a proof. The strategy we used to prove last theorem is called proof by contradiction. Mathematicians also call it reductio ad absurdum, which is Latin for reduction to absurdity. Basically we prove that some statement is true, by showing the opposite leads to a contradiction. We do the same thing on a daily basis. A blown light bulb doesn't light on, right? If we see it on, can't we conclude that the light bulb is not blown up? Yes. Because if it was, it didn't light on in the first place. Is the same thing with the previous theorem. X can't belong to the empty set because, if it did, the set wasn't empty. And now, it's time to grab your notepad again. Obviously two sets are equal to each other, if they have exactly the same elements. Let P be the set, orange, pear and plum, and let Q be the set, pear, plum and orange. P and Q have exactly the same elements, so we can say that the set orange pear and plum is equal to the set pear plum and orange, or simply P equals Q. Sets don't care about the order we write their elements. Sets don't care also about multiplicities of their elements. If Q was the set, pear plum plum and orange, P was still equal to Q. The set, orange pear and plum is equal to the set, pear plum plum and orange. Be careful when you're counting the elements of a set. The set are, orange pear pear plum 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 orange orange and plum, is equal to the set P, orange pear and plum. So, has the same cardinality. In this case, 3. Two sets are different if at least one of them has one or more elements that don't belong to the other. The sets P, orange pear and plum, and S, pear plum and banana, are different because the element banana belongs to S, but doesn't belong to P. So, the set orange pear and plum is different than the set pear plum and banana. Or simply, P is different than S. The orange and P would allow us to reach the same conclusion. The sets P and S of the previous example have the same cardinality. They are, however, different to each other. So, if two sets are equal, they have the same cardinality. But that doesn't mean that if they are different, their cardinalities are also different. The sets P and S are a counterexample of the statement, if two sets are different, their cardinalities are also different. This statement is false. If all the elements of a set are also elements of another set, we say that the first set is a subset of the second one. Let A be the set, Mars and Neptune, and let T be the set, Mars, Saturn and Neptune. All the elements of A are also elements of T. So A is a subset of T and we use the symbol to write A is a subset of T, or the set, Mars and Neptune, is a subset of the set, Mars, Saturn and Neptune. In the Euler-Venn diagram, we can place the set A inside the set T. Let now B be the set, Mars, Saturn and Neptune. The set B is equal to the set T. So, all the elements of B are also elements of T, and then B is also a subset of T, or the set, Mars, Saturn and Neptune, is a subset of the set, Mars, Saturn and Neptune. Let's place B inside of T. If at least one element of a set doesn't belong to another set, the first set is not a subset of the second one. Let C be the set, Earth and Neptune, and let T be the set, Mars, Saturn and Neptune. The element Earth belongs to C but doesn't belong to T. So C is not a subset of T, and we use the symbol to write C is not a subset of T, or the set, Earth and Neptune, is not a subset of the set, Mars, Saturn and Neptune. In the Euler-Venn diagram, we can place the set C partially inside the set T. As we saw, if two sets are equal, then one is a subset of the other. If a set is a subset of another set, but is different than that set, we call it a strict subset, or a proper subset. The set A, Mars and Neptune, is a subset of T, Mars, Saturn and Neptune. But, since A is different than T, A is also a proper subset of T. We use the symbol, or, to write, A is a proper subset of T. The set B, Mars, Saturn and Neptune, is also a subset of T. But, since is equal to T, B is not a proper subset of T. We use the symbol to write B is not a proper subset of T. Meanwhile, the set C, Earth and Neptune, is not a subset of T. So C is also not a proper subset of T. Let's make a theorem out of this. If a set is a proper subset of another set, then is also a subset. Symbolically, we say that if Q is a proper subset of P, then Q is a subset of P. Remember, a theorem requires a proof. Let's say a set is a proper subset of another set, but is not a subset. But then, there is at least one element of that set that doesn't belong to the other. But how can that be? The set was a proper subset of the other in the first place. We reached a contradiction by assuming that set was not a subset of the other. So, if a set is a proper subset of another set, then is also a subset. Let's make another one. If a set P is a subset of another set Q, and Q is also a subset of another set, R, then P is also a subset of the set, R. Symbolically, we have, if P is a subset of Q, and Q is a subset of R, then P is a subset of R. This theorem is a property called subsets transitivity. Let's prove it too. Let's say P is a subset of Q, and Q is also a subset of R, but P is not a subset of R. But then, there is at least one element of P that doesn't belong to R. Since Q is a subset of R, that element of P doesn't belong to Q either. But how can that be? P was a subset of Q in the first place. We reached a contradiction by assuming that P was not a subset of R. So, if P is a subset of Q, and Q is a subset of R, then P is a subset of R. The statements, if P is a proper subset of Q, and Q is a subset of R, then P is a proper subset of R. If P is a subset of Q, and Q is a proper subset of R, then P is a proper subset of R, and, if P is a proper subset of Q, and Q is a proper subset of R, then P is a proper subset of R, are also true. Can you see why? If A is a subset of T, we can also say that T is a superset of A. Let's revisit our examples. The set T is a superset of A. Since T is different than A, T is also a proper superset of A. The set T is also a superset of B. But since is equal to B, T is not a proper superset of B. Meanwhile, the set T is not a superset of C. So T is also not a proper superset of C. Can you explore the theorems we proved in terms of supersets? Grab your notepad again and answer to the following questions. Thanks for watching. And, until our next video, keep scratching the math.